Okay, welcome everybody. Now we have Tamara Kohler from Stanford University who will tell us about complexity and complexity.
Thank you. Yeah, thank you all for coming to my talk, and thank you to the organizers for inviting me to speak here today. So in today's talk, I'm going to be exploring how ideas from theoretical computer science, and in particular the concept of complexity, can give us insight into physical theories. So in complexity theory, the goal is to determine how much of a particular resource is needed to solve particular computational problems. And in today's talk, I'm going to be showing how by combining complexity theory with the theory of entanglement, we can study quantum gravity. Now, in today's talk, the way we're going to be probing quantum gravity is through the ADS-CFT correspondence. Now, I think a lot of the people in this audience understand ADS-CFT far, far better than I do. So I'm not going to try and give kind of a big introduction to the correspondence. But for those of you in the audience who aren't familiar with ADS-CFT, please don't switch off, because you really don't need to know a whole lot about ADS-CFT to understand this talk. So in order to follow this talk, really the only thing you need to know about ADS-CFT is that it's a duality between a theory of quantum gravity living in some d+1 dimensional space-time and a non-gravitational theory that lives on the boundary of that space-time. So we have kind of a toy cartoon picture of what's going on there in the slide. And the ADS-CFT dictionary, which is what we're going to be trying to understand in this talk, is just a map that takes us from states and observables and operators in the gravitational theory, so in the ADS side of the correspondence, to their dual objects in the non-gravitational side of the correspondence, so in the conformal field theory side of the correspondence. Now, as you might expect of a kind of a theory of quantum gravity, the ADS-CFT correspondence is pretty complicated. So there are some particularly kind of simple bulk geometries where the ADS-CFT dictionary is well understood. So given some, arbitrary bulk state in this simple geometry, it's well understood how to map that bulk state to a state on the boundary. And similarly in the reverse direction and for observables and operators. But that kind of detailed understanding of the dictionary is only currently known for pretty simple bulk geometries. And the idea of this talk is going to be to see if we can use tools from complexity theory to probe some properties of the dictionary. So, we're not hoping to come up with a full mathematical description of the dictionary. That's kind of a very optimistic goal that's going to be beyond the scope of this talk. But we're just going to try and use complexity theory to probe particular properties of the dictionary. So in particular, the types of questions we're going to be asking are, what is the domain of validity of this dictionary? What types of bulk states and boundary states can we feed into the dictionary and expect to get kind of a sensible, informative result out of? We're also interested in what are the entanglement and error correction properties of the dictionary. And in particular, we're going to be interested in the question, could this dictionary be efficiently implemented on a quantum computer? So this is kind of interesting from a theoretical perspective to understand the complexity of the dictionary. It's also interesting from a more practical perspective. So in this paper here by Safer Nizami and his co-authors, they came up with a proposal of how to really study quantum gravity in the lab based on the ADS-CFT correspondence. And their idea is that we should be able to simulate quantum field theories on a quantum computer. So given the ADS-CFT correspondence, we can hope to probe quantum gravity in the lab by simulating a conformal field theory on a quantum computer and using the ADS-CFT dictionary to look at what this simulation is telling us about the gravity theory. But this kind of idea really relies on the dictionary itself being something that we can implement on a quantum computer. Okay, so I've said the ADS-CFT dictionary sort of isn't well understood in general, but there are a few kind of entries in the dictionary that we might not know exactly how to map from one side to the other, but we know what sort of observable in the gravity side should map to an observable in the conformal field theory side. And for this talk, we're just going to be interested in two entries in the dictionary. The first entry is what geometry or kind of distance in the ADS side maps to in the conformal field theory side. And it's kind of a very long established result in ADS-CFT that distances in the ADS side of the correspondence should map to entanglement in the conformal field theory side of the correspondence. A more sort of recent and perhaps slightly less well established entry in the dictionary is that we expect wormhole volume in the ADS side of the correspondence to be dual to circuit complexity on the CFT side of the correspondence. Okay, so, I think the geometry equals entanglement entry here is very kind of well accepted by physicists. And the wormhole volume equals circuit complexity, there's maybe a little bit more uncertainty around that, but I think the idea that wormhole volume equals something like complexity is again pretty well accepted by the physics community. But for the computer science community, these entries in the dictionary raise some questions. And the reason for that is that on the ADS side of this dictionary, we've got two quantities that are easy to compute, or you might call them failable. And I hope I don't have to work too hard to convince you. Sorry.
You might say volume is easy to compute, but it's important that nobody can feel it. It can't be observed by anyone in space-time.
So I guess, yeah, I think I'll maybe come to this in a little bit. Yeah, no, I take your point. I think in Umesh's paper, they had a sort of algorithm to perhaps compute it efficiently. But I guess, yeah, we'll come to...
Compute it. If we have a solution of Einstein equation, you can compute the volume of the one, but no one in the space-time can measure it.
Okay. Yeah, I think maybe later in the talk we'll maybe come to this point in a little bit more detail. But thank you.
Circuit complexity, you are including non-unitary gates?
There could be, we could restrict unitary, or we could include all unitary gate. We could include non-unitary or not unitary. We'll see when we kind of go through the details of this part of the talk. The exact definition of complexity won't actually matter too much for the result.
I think it's correct that you would also not.
Okay, thank you. So I think the kind of confusion for complexity theorists comes because on one side of this duality, at least for the top line, we have something that's easy to compute, something you can feel and see. Whereas on the right hand of this dictionary, we have something that's hard to compute in general. We think, no one's come up with an algorithm that can efficiently measure entanglement or complexity. And this
correspondence frequently maps things easy to compute alongside the things that are hard to compute in others. What seems more relevant is that there's no experiment that measures entanglement. There's no experiment that measures circuit complexity, and here no experiment measures volume.
So I guess
that's part of the duality.
In Umesh and Bill's paper with Adam, they came up with sort of a suggested algorithm to measure wormhole volume.
Observers in space like that, but maybe I shouldn't have thought. But I don't think that's
okay. Well, yeah, I guess we're going to go through this as kind of a previous work, which I guess, yeah, there was some back and forth with the physicists. But we're also going to present some new work on the geometry and entanglement part of the correspondence, which maybe will go some way to kind of answering some of these discussions between physicists.
If the dictionary was efficient, then we could, there was only an assumption, then therefore we could the dictionary.
Something we could say is that if you believe the Hilbert space is belonging to the effective field theory, then there's a linear operator for one more volume. But in boundary theory, there is not a linear operator for the complex. You could say we could worry about that.
I don't have that to myself.
Okay, so this leads to some kind of intuition for complexity theorists that this dictionary seems to map hard to compute quantities to easy to compute quantities. So, does this mean that the dictionary itself is exponentially complex to compute? And if so, could this limit the utility of ADS CFT? And in particular, this would mean the kind of quantum gravity in the lab idea that I mentioned a couple of slides ago really wouldn't be feasible because, okay, you can do the simulation efficiently on a quantum computer, but that will just tell you about the conformal field theory side of the correspondence, and you won't be able to use the dictionary to find out about the gravity side of the correspondence. So this is kind of the complexity theorist intuition based on the kind of entries of the dictionary I mentioned in the previous slide. But this really doesn't mesh with the physicist intuition for what's going on. So physicists say that the dictionary really should be efficient for simple geometries, And indeed, they have examples where the dictionary is efficient. And this kind of raises the question, or I guess the answer from physicists, that the complexity theoretic arguments that I've kind of sketched might not apply to certain states. And that's a very reasonable sort of answer. In complexity theory, we're typically interested in worst case complexity. So how hard is the hardest problem of this type? But, for any hard problem, you can typically find easy instances of that problem. So it could well be that for the states of interest in ADS-CFT, there is an efficient method to measure entanglement or complexity. But, there also might not be. This is an interesting open question. So the central question we're going to be interested in this talk is when and where is the ADS-CFT dictionary exponentially complex? And the tools we're going to be using to tackle this question are, complexity theory and entanglement theory. And the goal, kind of overarching goal of this talk is to, first of all, present some complexity theoretic work to try and formalize the intuition about the complexity of the dictionary, and also give some kind of summary of the physicist responses, and I hope I'll do justice to the physicist point of view as well. And I'm going to attempt to demonstrate that this line of research is leading to a really productive dialogue between computer science and physics. I'm also going to present some upcoming work showing that ADS-CFT might be complex to compute in relatively simple geometries. And the goal of this upcoming work isn't to kind of end this line of questioning. It's really, a piece of work that we think leads to many more interesting open questions. So hopefully I'll convince you that there's lots of interesting stuff to work on in this area. Okay, so to start off with, I'm going to present some previous work due to Adam Boland, Bill Pfefferman, and Umesh Vezirani. And this was sort of the first, I guess, work by complexity theorists trying to formalize the intuition that the dictionary seems to be mapping hard to compute quantities to easy to compute quantities, and that this might say something about the complexity of the dictionary. So this is sort of tackling the second entry in the dictionary here. So the idea that the volume of a wormhole is equal to the complexity of a CFT state is a conjecture due to Lenny Susskind back in 2014. And I guess the kind of intuition for the conjecture is that in ADS, it's expected that the volume of a wormhole will grow for exponential time. And there aren't many quantities on the CFT side of the correspondence that we expect to grow for exponential time, because the CFT side of the correspondence is meant to be kind of highly scrambling, so you'd think most properties would equilibrate in polynomial time. But the complexity of a CFT state is something that could grow for exponential time. And that was kind of, I think, the intuition behind this conjecture. And, again, from a physicist's point of view, this conjecture seems very reasonable. But from a complexity theorist's point of view, this doesn't seem so reasonable necessarily. And that's because complexity theorists think that circuit complexity should be hard to measure in general due to pseudorandomness. So there have been some really nice talks on pseudorandomness earlier in this conference by Robert yesterday and by Fermi last week. For the purposes of this slide, pseudorandomness is relevant because the existence of pseudorandom states demonstrates that there are states that can be prepared efficiently, but that cannot be efficiently distinguished from truly random states. And truly random states can't be prepared efficiently. So that tells us that we have classes of states where there is no way to tell how complex they are, how many operations it takes to generate them. But this kind of second bullet point here doesn't necessarily imply that there's anything strange going on with the complexity equals volume conjecture, because pseudorandom states are not kind of generic. The pseudorandom states constructions we have are fairly specialized. And the kind of key question here is, does pseudorandomness appear in states considered in the complexity equals volume conjecture? And that was a question that the BFE paper tried to answer. So in BFE, it was shown that you can construct quantum pseudorandomness out of wormholes using shocks. So the idea here is that the state on the boundary of ADS-CFT, which is dual to a bulk state containing a wormhole, isn't pseudorandom itself. But from this boundary state, you can construct a state that is pseudorandom by applying a sequence of random shocks. And the idea here is that these states are pseudorandom, and that means that kind of by definition, their complexity can't be measured efficiently. And that begins to raise some questions about the complexity equals volume conjecture. I should also say that their result kind of implies something slightly stronger, and that's that it's possible to create states with totally different wormhole lengths, which aren't efficiently distinguishable. And that means that it doesn't matter exactly what the dual is to wormhole volume in the CFT. Whatever it is, it's something that's difficult to compute in the CFT, because if it wasn't difficult to compute, we would always be able to distinguish states with different wormhole lengths. And this led to kind of the implication in the BFE paper that ADS-CFT is exponentially complex to compute. And I have kind of a toy model of this, which I think might be a little bit oversimplified based on Ed and Umesh's comments. But the toy model is that you can potentially measure the complexity of a CFT state by starting off with some CFT state, applying the dictionary to have some state in ADS, measuring the wormhole of the state in the ADS space to get the volume of the wormhole, then applying the dictionary again to give the complexity of a pseudorandom state. And I take, at Umesh's point, this isn't exactly how it works, but in the BFE paper, they do have a construction showing that if the dictionary is efficiently computable, then this implies that the wormhole volume is efficiently computable. And since we know the complexity of a pseudorandom state isn't efficiently computable, this kind of implies a contradiction. Okay, so where does that leave us? Well, we have that the wormhole volume is easy to compute if the dictionary is efficient, but it's dual to something that's hard to compute in the ADS side, in the CFT side. This thing is something like complexity, but it doesn't matter exactly what it is. We know that it must be hard to compute. And this gives rise to the conclusion that the ADS-CFT dictionary itself must be exponentially complex to compute. So this was sort of the first kind of attempt by computer scientists to use complexity theory to look at the properties of the ADS-CFT dictionary. And the physicist's response was essentially fantastic. These results show that it's difficult to apply the ADS-CFT dictionary inside a black hole, which is expected. But the kind of implication was a similar hardness result shouldn't be possible in geometries without black holes. And this is a kind of a nice intuition, because it suggests that black hole horizons protect Church-Turing. So for those of you who aren't familiar, the extended quantum Church-Turing thesis essentially says that the only computations that should be possible to do efficiently in nature are those that can be done efficiently by a quantum Turing machine, or an efficient quantum circuit model. And if you could compute, if you could use the dictionary to compute things outside of what you can do efficiently on a quantum computer, this would violate the extended Church-Turing thesis, which I think would be an uncomfortable situation for computer scientists, at least. But in this paper by Susskind, he argued this doesn't happen because the existence of the black hole horizon really protects the Church-Turing thesis. Someone who kind of jumps into a black hole might be able to compute things outside of what you can do efficiently on a quantum computer, but that information isn't accessible to anyone outside the black hole, and in particular, it's not efficiently accessible to someone who just has access to the boundary of ADS-CFT. Okay, so to explain what the source of the complexity is in geometries with black holes, I'm going to do a short digression for people who aren't particularly familiar with ADS-CFT to discuss minimal surfaces in ADS-CFT. So for this slide, you should imagine that what we have here is the ADS, the bulk theory, the gravitational theory, is the inside of the circle, and the boundary theory is the boundary of the circle. And in this picture, we split our boundary into two regions, A and A complement. And the minimal surface of A, or equivalently of A complement, is defined as a surface which has the same boundary as A, which goes through the bulk and is the minimal such surface. And this is a slight simplification, but for people who aren't familiar with ADS-CFT, we can think that the bulk region that can be reconstructed on a particular boundary region is the region that's bounded by A itself and the minimal surface of A. So, for example, in this picture, we have that phi of x is reconstructible on A, but it's not reconstructible on A complement. Okay, so that's just a short digression for anyone who's not familiar with ADS-CFT. But now back to the main point. What's the source of the complexity in geometries that don't have black holes? So one possible answer to this question was suggested by Adam Brown and co-authors back in 2019. And it's what's known as the Python's lunch conjecture. And the original Python's lunch conjecture suggests that in geometries that contain a Python's lunch, you should expect to find that the dictionary is exponentially complex for some parts of the reconstructible region. Okay, so let me explain what I mean by that. In this picture, I want you to imagine that our boundary is here on the right-hand side. So we're interested in what parts of the bulk can be reconstructed on this right boundary. Now, from the previous slide, we know we should be able to reconstruct anything which lies between this boundary and the kind of minimal surface in the bulk. And I mean, this is a bit of a toy picture, but here this minimal surface is given by this AL over here. It's smaller, it's kind of the smallest, the thinnest part of this bulge is given all the way over here in AL. But this A right line over here, this is a locally minimal surface. So you have, your bulk kind of getting, after this, it starts getting fatter for a bit, and then eventually it thins down into its actual minimum. Now, we should expect that the bulk region that's reconstructible on this boundary region should be everything that lies from AL all the way to the boundary region. What the Python's lunch conjecture says is that even though this entire region is reconstructible, the region that lies between AR and AL shouldn't be efficiently reconstructible. So the Python's lunch conjecture argues that everything from AR to the right should be efficiently reconstructible on the boundary, meaning that if you have access to the boundary theory and a polynomial time quantum computer, you should be able to probe the bulk in this region. But it says that everything that lies between AL and AR will only be accessible to you on the bulk if you have some exponential time quantum computer. So the original Python's lunch conjecture just said that the area between AL and AR should be hard to reconstruct. The strong Python's lunch conjecture says that this is the only source of exponential complexity in reconstructing the ADS-CFT dictionary. So the strong Python's lunch conjecture argues that if you don't have this sort of bulge geometry, then everything that's reconstructible in a particular boundary region should be so efficiently. Okay, so what's the intuition for this? I've just told you you have some bulges and this makes things hard and easy, but where does that come from? So the intuition comes from tensor network toy models of ADS-CFT. So you should think of this as really being a tensor network toy model of this geometry. So wherever we have that this geometry is sort of fixed width, we have that represented by unitary tensors in our tensor network. Wherever our geometry is expanding, we can represent that by isometric tensors. So these tensors have more inputs and outputs, and that leads to the geometry bulging. We then again have a unitary portion of constant width, and then we have the portion of our geometry where the geometry thins down. And we can represent that by the inverse of isometries. So inverse isometries have more inputs and outputs, and that leads to this constriction in the width of our geometry. Now, why should this constriction in width make reconstruction difficult? Well, if we consider, again, we're going to be wanting to reconstruct something on the right-hand side of this diagram that was input on the left-hand side. So it's straightforward to see that the first few steps here are going to be efficient to compute. if we start with a quantum state here, input on the left side, the first few layers are just a layer of local quantum gates. Yeah. So yeah, I'm going to assume that what the overall, yeah, so it should be approximately isometric, which can be shown it will be true in general. Yeah, but obviously not each step is necessarily. Yeah. So yeah, we start off with some local unitary gates, clearly efficiently to implement on a quantum computer. We then have some isometric tensors, again efficient to implement. You just add in some ancillas in the 0 state and apply local quantum gates. Another row of unitary gates, again clearly efficiently to implement. And then we get to the interesting bit. We get to these inverse isometries. And, you know, in order to, the kind of most straightforward way to implement an inverse isometry on a quantum computer is to extend this to a unitary and apply the unitary. But this won't, and then you have to kind of measure your ancilla qubit that you formed as part of your extension. And if the ancilla qubit, all the ancilla qubits for all of these inverse isometries are in the 0 state, then you can accept that your computation has worked. You've correctly applied these inverse isometries. But if any of your ancillas after this step aren't in the 0 state, that means that you haven't correctly applied this inverse isometry. And that will happen with high probability. Yeah. Yeah. Yeah, maybe, yeah, that may be the case. So yeah, this is kind of the intuition between the Pythons behind the Python's lunch conjecture. But yeah, I guess maybe this needs some. Yeah, so you should be able to preserve information from here to here by the Python's lunch conjecture. Yeah. So sorry, Norbert's point is that if the overall thing is approximately isometric, then these post-selections should succeed with high probability.
No, that's not the right way to think about it. It's just a linear. So you might have to rescale. You may have to rescale the network a bit in order to get the approximate isometry.
So sorry, Dan's saying you might have to rescale it. Then you should consider it as a linear map. So you might have to rescale the network to get.
Yeah, you rescale it. So the idea is that whatever you state in from the state you send in from the left, you kind of lose an equal amount of the north. So then you just rescale to get that.
Okay, thank you. So the idea is that these post selections will fail with high probability, and that means you'll have to run this circuit many, many times in order to get the output you're looking for. And that means that when you have these shrinking geometries, you shouldn't expect to be able to implement this circuit efficiently. Okay, so this is kind of the intuition behind the Python's lunch conjecture. I'm also going to make the point that telling whether or not there's a Python's lunch in your geometry isn't necessarily completely straightforward. So what we have here is a unitary circuit that contains some randomness. So these, you should consider in this image that the U and U prime here are fixed unitaries. You know exactly what they are. But the UK here, these are sampled from some set of random unitaries. So we have, for each key K, we're going to apply a different random unitary. Now, if you just look at this circuit, you'd think there's no Python's lunch geometry here. there is no minimal surface, everything's just fixed width. So, there's no Python's lunch. But that's a bit too simplistic. And the reason for that is that in ADS-CFT, when you're considering whether or not your geometry has a Python's lunch, you can't just pick a particular boundary state to do this. You have to consider kind of a distribution over all the states on your boundary. And what that means is, for any particular choice of random unitary k, and therefore for any particular boundary state, this circuit doesn't contain a Python's lunch. But if we want to consider the distribution over boundary states, we need to take into account the fact that, this random unitary k has some input to it, which picks which of the unitaries we're going to apply. And the way that it's suggested that you take this into account when trying to decide if your geometry contains a Python's lunch or not is by treating the choice of which random unitary we apply as an input, where you should consider each of these input legs to essentially have a number of qubits which is equal to the key length in binary. And by doing this, you're kind of taking into account all the distribution over your boundary, over the possible choices of boundary states that might arise as a result of the choice of which unitary to apply. Okay, so when you do this, you can see kind of straightforwardly in this picture, you do get a Python's lunch. So, the AR and AL here are equal, but introducing these bits which control the choice of unitary have kind of fattened out the geometry at the point just before we apply these unitaries, and that's given rise to a Python's lunch geometry. And in this paper, due to Netta Engelhardt and her co-authors, they kind of analyzed the BFE construction using this kind of insight about randomness and how to take into account randomness in ADS-CFT. And they argue based on this that in the BFE construction, there is a Python's lunch. And in a separate paper, also by Netta and co-authors, it's shown that Python's lunches must lie behind event horizons. So therefore, if you accept the strong Python's lunch conjecture, this implies that the ADS-CFT is only exponentially complex if the bulk contains a black hole. Oh yeah, so the strong Python's lunch conjecture says that the only source for exponential complexity in the ADS-CFT dictionary is a Python's lunch geometry. So the only time you should ever have an exponentially complex dictionary is when you're in this region, kind of in the bulge of a Python's lunch. For all other geometries, the map should be efficient. And then pairing this with this kind of result suggests that the only source of complexity comes from black holes. In the ADS part. So yeah, this geometry is kind of in the ADS and the boundaries are given here. So here's your mapping from the bulk, you're mapping it out towards the boundary. And when you get this constriction, that causes exponential complexity. Is that clear? Yeah, so you should think of just kind of filling this in with a circuit, and your circuit is trying to map from this AL all the way to this boundary, and you can kind of, from here to here, you can map efficiently because everything's expanding, but when you're trying to map information from this region out to the boundary, you're having to go through this kind of inverse isometry. There are more efficient ways to do it than post-selection, but there aren't much more efficient ways. So therefore, going through this constriction creates complexity in the dictionary. So you think of that circuit as kind of being our attempt at constructing a dictionary. Okay, so the complexity theorist's intuition to this is, why should we need black holes to do cryptography? Pseudo-random states are a very kind of weak primitive for quantum cryptography. So it seems strange that we can't do them without black holes. We know that you can instantiate cryptography with weak models of computation. So using log-log depth circuits, you can instantiate cryptography. And can't you just think of gravity without black holes as a weak model of computation? Why should that prevent you from doing cryptography? But obviously, you're not going to be able to probe this. You're not going to be able to probe the complexity of the dictionary without black holes by using the wormhole equal volume conjecture, because wormholes are always going to appear in the presence of black holes. So that raises the question, is there another basis for arguing the difficulty of the ADS-CFT correspondence? And this line of thinking launched a kind of a new branch of quantum pseudorandomness, which is based on hiding entanglement. And this branch of pseudorandomness is known as pseudoentanglement. So just to kind of recap, the reason we're interested in hiding entanglement is because of this first entry here in the dictionary. So this first entry says geometry is dual to entanglement. And for people who aren't kind of very familiar with ADS-CFT, this arises because of the Root-Akianagi formula. And this formula says that the von Neumann entropy, so the entanglement entropy between the A portion of the boundary and the A complement portion of the boundary, is proportional to the area of this minimal surface, where this minimal surface is the same one that was defined a few slides ago. Okay, so this gives a kind of a very nice concrete sort of relationship between entanglement and geometry. Now, if we can show that entanglement is hard to compute, this might give a method to argue for hardness of the dictionary without needing to have wormholes, and therefore potentially without needing to have black holes. Okay, so what do we want from a pseudo-entangled state? Well, as the name kind of suggests, we want it to be a state that looks highly entangled, but isn't. And this will show that entanglement can be cryptographically hidden. So, we can have entanglement in a quantum state that we can't probe, can't measure. And this could be the basis of the hardness of the ADS-CFT dictionary, because the ADS-CFT dictionary is meant to make entanglement feelable by mapping it to distances which should be measurable. Okay, so how do we define pseudo-entanglement a little bit more rigorously? So in order to define pseudo-entanglement, we're going to need to have two state ensembles. One state ensemble will denote by psi low and one by psi high. Now, in order for this pair of state ensembles to be a pseudo-entangled, we're going to need there to be an entanglement gap between them. So we're going to say that all psi high have high entanglement and all psi low have low entanglement across some specified set of cuts. We're also going to need this, both these sets of states to be efficiently preparable. So when I say efficiently preparable, I mean they should be preparable by a quantum computer acting in polynomial time, starting on some product input state. And this efficient preparation is important because we're going to require that these states are computationally indistinguishable. So that means that no efficient quantum computer should be able to distinguish polynomially many copies of a state from psi high from polynomially many copies of a state from psi low. And in order for it to be clear that this computational indistinguishability isn't just an artifact of the fact that these are very complex states, we need that the states themselves are efficient to prepare. So this is kind of closely related to the concept of a pseudo-random state. But yeah, it's a kind of a new branch of pseudo-randomness that really was inspired by this attempt to study the complexity of the ADS-CFT dictionary. Okay, so we can define pseudo-entangled states, but can we actually construct interesting examples of them? And how much entanglement can we hide? So we're going to be working in a regime where we're going to take entanglement on a scale of 0 to n, where n is the number of qubits. So we're working in kind of log of base 2. So the first result on quantum pseudo-entanglement demonstrated that there exist pseudo-entangled pairs of state ensembles where the psi high have maximal entanglement across a particular bipartition, and the low entanglement is separated from this by a constant gap. This was improved upon in kind of the second result on quantum pseudo-entanglement, where it was demonstrated that there exist pseudo-entangled states where the high entanglement state ensemble is again maximally entangled, but the low entanglement state ensemble has entanglement which is kind of just slightly more than log n across every bipartition. And this really is kind of the best general result you can hope for, because if you have entanglement less than log n, you can efficiently test that. So this really shows that it's possible to get the maximum entanglement gap, and it's possible to get that across every bipartition of your state.
Why here is the computations between n minus order 1 and versus log n?
Sorry, I didn't catch the first part.
Why there is a computation for the gap? So you have mentioned that there is a gap n for gap n minus order 1.
Yeah, so sorry, the gap, so that means that this is the entanglement of the high entanglement state, and this is the entanglement of the low entanglement state. So the gap is just the distance between the entanglement of the two state ensembles. Thank you. Okay, so what does this existence of these pseudo-entangled states say about the ADS-CFT dictionary? So far, not much. And the reason for that is that these initial pseudo-entangled state constructions didn't obey the Routak-Yanagi formula. So, you're still left with the question, well, maybe all states that are holographic have simple to measure entanglement, and maybe this pseudo-entanglement idea just doesn't apply to the states we're interested in holography. So in order to kind of push to being able to say something about the ADS-CFT dictionary, we need to come up with a construction which does look holographic. And we do that in this upcoming work. We're going to now turn to look at this construction of holographic pseudo-entanglement. Okay, so the main result of this forthcoming work is that it's possible to construct pseudo-entangled states which approximately obey the RT formula for certain geometries. And the techniques we use to construct them are actually both techniques that have been spoken about this week. So we're going to use tensor network toy models of ADS-CFT, which Daniel Harlow kind of covered nicely in his talk. And then we're going to use new constructions of pseudo-random unitaries, which approximately preserve entanglement, which Robert Huang covered in his talk. And the nice feature about these holographic pseudo-entangled states is that it seems like these geometries might not contain horizons or Python's lunches. So there might be some conflict here with gravity intuition about when the dictionary is hard to compute. Okay, so if you recall from Robert's talk yesterday, it's possible to construct pseudo-random unitaries from a brickwork construction. So what I mean there is that if each of these U1 and U2 are short depth pseudo-random unitaries, then this construction here, given by a brickwork construction of applying U1 and U2, is itself a pseudo-random unitary, where we require that each of these legs here is actually a collection of log n qubits. And what's really nice about that from our perspective is that because these pseudo-random unitaries are generated by short-depth quantum circuits, that means that they approximately preserve the entanglement of the state they act on. So this kind of gives a whole new family of pseudo-entanglement constructions, where you just apply this brickwork construction to any product state, and the state you get out will be pseudo-entangled. And that's because the state you get out will be computationally indistinguishable from Haar random states based on the definition of a pseudo-random unitary, and therefore will be computationally indistinguishable from highly entangled states, even though its entanglement will be upper bounded by log n. Okay, so for our purposes, we're going to need a slight modification of this brickwork construction. And we're going to need to move away from pseudo-random unitaries and instead look at pseudo-random isometries. And a pseudo-random isometry is just a pseudo-random unitary where now you fix some of the input qubits to be in the 0 state. And it turns out that you can do kind of exactly the same sort of brickwork construction for pseudo-random isometries that you could do for pseudo-random unitaries. So that means if you have a collection of pseudo-random isometries, you can apply these pseudo-random isometries on a small number of input qubits in this brickwork fashion, and that gives you an overall pseudo-random isometry. Okay, so with that background of pseudo-random isometries, we can look at how we construct this holographic pseudo-entanglement. So we're going to start off by taking an efficiently constructible tensor network toy model of a holographic state. So in Dan Harlow's talk on Monday, he introduced tensor network toy models of ADS CFT, which are built out of perfect tensors, where perfect tensors are just tensors with very nice properties. I won't go into what they are here. He also mentioned in his talk that he actually prefers the construction based on random tensors. And I think maybe part of the reason for preferring that construction is that a construction built on random tensors gives a better approximation to the RT formula than a construction built on perfect tensors. Now, for our purposes, a construction built from truly random tensors is problematic because a truly random tensor network can't be constructed efficiently on a quantum computer. But luckily for us, there's kind of a happy medium where you get the best of both worlds, and that's using random stabilizer tensors. So if you use random stabilizer tensors, you get the nice entanglement properties of using random tensors, but you also get that these tensor networks can be kind of instantiated efficiently on a quantum computer because random stabilizer tensors can be kind of built efficiently, constructed efficiently using Clifford circuits. Okay, so this is the first step of our holographic pseudo-entanglement construction. And then all we do is on the boundary, we apply the brickwork pseudo-random isometry construction. Now, the kind of crucial thing here is that this pseudo-random isometry construction doesn't change the long-range entanglement of the boundary. So in fact, you can show that this gives kind of very small corrections to the RT formula. And I mean, we conjecture, although we haven't shown it rigorously yet, that in fact you can show that this kind of larger tensor network does exactly obey the RT formula, just for a slightly modified geometry. But even though this state is still kind of approximately or perhaps exactly obeying the RT formula, it's now computationally indistinguishable from a Haar random state. And I say there is also a paper by Netta Engelhardt that has a different construction of holographic pseudo-entanglement, and also forthcoming work from UT Austin, which will also have a different construction. Okay, so what's nice about this construction here? Well, again, we can look at how we might try and measure entanglement using the ADS Cft Dictionary. So we can start off with some state in the conformal field theory, apply the dictionary, and end up with a state in ADS. By measuring distances in this ADS space, we're going to get some information about the geometry of the bulk. And in particular, we can determine the length of some minimal surfaces. We apply the dictionary again to this information about the bulk geometry, and that will give us the entanglement of a pseudo-entangled state. Now, this is obviously just a toy model. We don't actually have a CFT or an ADS space. We've got tensor networks. But if applied to real ADS CFT, it applies that some step in this process must be doing computation outside of BQP, because we know that measuring the entanglement of a pseudo-entangled state is not possible in quantum polynomial time. Therefore, some step in this procedure is doing a computation that isn't possible in quantum polynomial time. Okay, so I claimed that our construction doesn't contain a Python's lunge. How can we see that? So we're going to look at just a kind of small toy model of a couple of tensors in this tensor network. And we're going to start with the tensor network itself. And then we can look at applying 2 layers of PRIs at the boundary. So what's nice about these PRI constructions is that we don't have to add loads and loads and loads of randomness into this construction in order to get a holographic pseudo-entangled state on the boundary. And what I mean by that is that we do 2 layers of these pseudo-random isometries, and in each layer we can use the same pseudo-random isometry. So we have this large distribution of pseudo-random isometries, and we only have to pick 2 elements from it. We then apply one of these elements to pairs of outputs, pairs of kind of boundary legs in our tensor network, and then we apply the second isometry that we pulled from this distribution. And again, we now apply this isometry to kind of overlapping outputs from the first round of pseudo-random isometries. Okay, now if you remember from kind of earlier in the talk, I mentioned that when we have randomness in our construction, we have to be very careful to take that into account when deciding whether or not our construction contains a Python's lunch. So we're going to add input qubits to each of these pseudorandom isometries. And these input qubits can be thought of as kind of containing the information about which isometry from our ensemble of pseudorandom isometries we're going to apply at each point. And now, the key for the pseudorandom isometry is fairly long, but because it's the same pseudorandom isometry being applied many times in parallel, we kind of don't have to add this key in every time. We can kind of split the key over the pseudorandom isometries, and it's kind of one lot of randomness being added into each layer of the tensor network. And if you kind of look at the cuts through the tensor network, once you've added these, once you've added in the extra qubits, input qubits, to take into account of this randomness, you can show that for appropriate choices of parameters, we can construct a network where there isn't a Python's lunch in this geometry. So by that I mean that this kind of, the geometry is shrinking monotonically. We don't have any bulges. And that seems to imply that this tensor network construction doesn't contain a Python's lunch. It's really crucial here that we're using pseudorandom isometries rather than pseudorandom unitaries. If we just applied the pseudorandom unitary construction that Robert presented in his talk yesterday, we'd find that when we add in these additional legs to take into account the randomness, we would definitely get a Python's lunch construction. And that is kind of seen from the example I presented earlier. If you have unitary circuits with some randomness, they just almost by definition are going to lead to Python's lunches. But using pseudorandom isometries allows us to bypass this. It's also important that we can apply the same pseudorandom isometry in parallel. So if we needed for each of these isometries to be different pseudorandom isometries, we'd be adding in a large amount of randomness into our model at each step. And although we could do that without having a Python's lunch construction, we'd have to do it in a way where we end up with kind of massively expanding the boundary Hilbert space in a way that, it kind of loses the connection to the original tensor network we started with. But because we can apply these PRIs in parallel, we're only adding a small amount of randomness at each of these two steps. So, we don't think that our construction contains a Python's lunch based on previous work on Python's lunches in the literature. I should say that this implies that our construction is violating at least one of the assumptions from this paper by Netta Engelhardt and her co-authors, which is called, I think, Spoofing Entanglement in Holography. So in this paper, the authors make 4 assumptions about ADS-CFT. And based on these 4 assumptions, they demonstrate that pseudo-entangled holographic states are always dual to Python's lunches. So I think trying to, understand which one of their assumptions is violated by our model is kind of an interesting open question. Okay, so where does that leave us? We have holographic pseudo-entanglement without Python's lunches. What does this mean? So the kind of nice thing about this construction is that we can start off with any 2 tensor network geometries. I have one tensor network geometry that corresponds to a fairly flat geometry, and another tensor network that corresponds to a very curved geometry. We can then apply our kind of pseudo-random isometry brickwork construction to the boundaries of these tensor networks. And using that pseudo-random isometry brickwork construction, we can make the boundary states corresponding to these 2 very different bulk geometries computationally indistinguishable. And where does that leave us? So we've got bulk geometry, which I think, I personally think we all agree, bulk geometry should be easy to compute. It shouldn't be hard to measure distances in ADS. But this is dual to boundary entanglement, where now we can show, at least in toy models, we really can construct holographic boundary entanglement, which is hard to compute. And that suggests that, okay, this is a toy model, but it suggests that the ADS-CFT dictionary might be complex even in the absence of Python's lunches or black holes. Okay, so I said that one of the goals of this talk is to convince you that there's interesting open questions to work on here. And really, all of the open questions here are basically just trying to understand where's the conflict between physics and computer science? What's the root of this sort of disagreement? So one possible suggestion is that really physicists and complexity theorists are just sort of talking at cross purposes and working in different input-output models. Now, in computer science, our input is just the boundary state. We're saying you're not given any information about the bulk geometry or the bulk state at all, you're just given the boundary state. Now, can you tell me the entanglement structure? In physics, it seems from the physics papers, you are given the boundary state, but often there seems to be some kind of implicit or sometimes explicit assumption that you also have some information about the bulk geometry. So for example, in the HKLL algorithm, I think you know the boundary geometry and you're computing fields around that geometry. So is this kind of just talking across purposes? Would physicists generally say that generally they expect to have some information about the bulk geometry? And I should say this also seems to kind of match up nicely with the Python's lunch conjecture. The Python's lunch conjecture does seem to imply that the reason it's easy is because you know the circuit you're applying, and in tensor networks, knowing the circuit is sort of equivalent to knowing the geometry. This could be the reason for the mismatch. I think if this is the reason, it's still a really interesting research question, because I don't think this just means, okay, we're just talking about different things, there's no conflict. It means, okay, we're talking about different things, and that might explain, why our result is different to the result of Netter et al. But I still think there's then an interesting open question about how does bulk geometry emerge from the boundary theory? So in Daniel Harlow's talk on Monday, he spoke about how we should see space-time as an emergent property. But if space-time is emerging from entanglement, and the dictionary is complex, does that mean that kind of the emergence of space-time is itself an exponentially complex process? Okay, so that's kind of one potential explanation for the difference between the physicist and the computer scientist intuition. Another one is that maybe there's a hidden Python's lunch in our construction that we've missed. So we took into account the randomness, but I think Python's lunches are relatively new, I think, as concepts. So there might be some other reason why there's a Python's lunch in our construction that we haven't picked up on yet. I think this could be an interesting kind of thing to look at to try and understand the Python's lunch conjecture better. Another potential answer might be that, a physicist might say that our result is just an artifact of the tensor network construction. This would, I think, be the least interesting outcome, but I also think it's the least likely one. And the reason for that is we use tensor networks in our construction in order to give a boundary state that obeys the Ruta-Yanagi formula, which we can then apply our brickwork PRI construction to. But the only reason we use tensor networks is just to have a concrete example to work with. In some of the other examples of holographic pseudoentanglement, which are coming out, which are forthcoming, they do really use the tensor networks to construct the pseudoentanglement. And there you can kind of see, it's not clear how to apply that construction in real ADS-CFT. So maybe you could argue, well, these results shouldn't apply to real ADS-CFT. But here, as I said, the tensor network is just there as a tool to construct a holographic state to start with. The way we turn a holographic state into a pseudo-entangled state is very generic. It just relies on the existence of pseudo-random isometries. And I can't see any kind of immediate reason why you can't apply the same pseudo-random isometry trick to a true conformal field theory state. And so I think if this is the answer, I think we do need to pin down why doesn't our construction work in a real ADS-CFT. And the final kind of possibility is that maybe there are other types of geometric constructions to efficiently reconstructing bulk operators in the boundary. So this would apply that this wouldn't contradict the original Python's lunch conjecture, but it would suggest that the strong Python's lunch conjecture isn't true, and that there are other types of geometric obstructions to efficiently reconstructing bulk operators. So that's kind of all I had to say, but happy to take any questions.
Yeah, unfortunately, Netta could ask this question better than me, but I'll try. So in real ADS CFT, if you don't have a black hole, then we naively think that by using the HKLL procedure, you can reconstruct everything efficiently. So is there? Yeah, so I guess in these examples you were saying, I guess I would have thought that that's what would happen. I mean, maybe, but I don't know if there's enough structure here to have something like this.
Yeah. I guess, I don't know if this is exactly an answer to the question, but maybe it helps. So I guess, I think the intuition for the Python's lunch conjecture, I think the reason this is kind of failing, the Python's lunch conjecture intuition is failing, is because here at this step, each of these, before we added the initial random key here, each of these tensors is isometry. But when we add the random key, these aren't unitaries. They map n legs to n legs, but they're not unitaries. So that means we can't, the reason we can't just run this circuit backwards and find out what key was applied and find out, what our boundary state is that these don't have to be unitary, even though the original tensor is isometric.
Let's see, so if I have say I have some operator that acts on one of those legs from the left,
I can't just push it through those V's.
Oh, so from the left to right, you can push it through?
The left is.
Yeah.
Right, so if I have some operator in the bulk and I'm going to turn it into a boundary reconstruction, I thought I'm just supposed to push it through.
Yes, you can push through in this direction. It's going the other direction that's hard. So if you just have the boundary state, determining the bulk is difficult.
sorry, no, I thought what I do is, so say I want to, say there's this spin somewhere in the bulk, whether it's up or down, right? So that's a bulk operator. So that's an operator that acts on one of those left legs.
Yeah.
Okay. But I can turn it into an operator that acts on the boundary by pushing it through from left to right.
Yeah, and you can.
Now in the boundary theory, I just measure that operator. And isn't that operator not exponentially compliant?
So the issue is you don't know what this key is. So you don't know what the correct bulk boundary operator is.
Oh, well, maybe this is one of those things. But sorry, so you discussed this before, right? Then don't you have to include the reference system that's entangled with the randomness?
Or whatever.
Yeah. And I think even with that, people don't get a Python's lunch.
But you say if I include those, then I now can't push.
If you know what the key is, then you can efficiently tell them apart. So this only applies if you don't know what the key is.
I guess in my opinion, it's just the other situation. We know
So you know the code space, so that doesn't necessarily imply that you know. Yeah, so these V's, so these V's would change the code space. So this is again maybe somewhere, we haven't got a construction of these that preserve the low energy subspace of the Hamiltonian. That is something we're interested in, but we don't have it yet. So here, yeah, it's true. You don't know. The code space here has been kind of messed up.
it's like you have a bit of noise in holographic.
Yeah.
Yes, that's a different setting.
Yeah.
Could it be that in this picture, it seems like there should be a horizon. There should be a horizon. All that stuff is showing there inside the horizon.
So I guess then you'd be arguing there's a horizon kind of right, like the whole bulk is inside a black hole. Yeah, I mean, I guess this would still, I guess, contradict the Python's lunch conjecture, the strong Python's lunch conjecture. Potentially, unless there's another way of constructing a black, unless there's kind of a hidden Python's lunch in here.
Other external system. Like I'm just thinking that in your construction, you have some finite dimensional Hilbert space on the boundary, I guess, and then you can talk about these hard random operators. And from the holographic perspective, that would create some, it's kind of like creating some infinite temperature state where the horizon was way out near the boundary. And so if we make a different if we try to account for that in your model, we should not try to make it look like hard random. We should think about it as somewhat random in some lower energy subspace. Then maybe the structure would be moved into the tensor network a little bit and would be behind the horizon.
Yeah, I mean, I think it's possible there's a black hole here. I don't see exactly where the black hole is coming from.
These very complicated tensors that raise the energy a lot. These D, A, that make the state locally hard random. Those should raise the energy of the boundary state by a lot. Maybe in the bulk, it's like we have some kind of shell high energy stuff out of unit and then come up with the graduate horizon.
Yeah, I think we haven't kind of exactly ruled out a black hole. I think we can rule out, well, based on the current constructor, we can rule out a Python's lunch, but ruling out a black hole is.
Well, I'm not totally sure about ruling out the Python's lunch in this setting because that might depend on the geometry sort of between the horizon and the boundary. I'm not sure that part is accurately reflected in this picture.
Okay, it would definitely be interesting to chat about how to modify it.
I mean, you can have a black hole without having a Python. For example, each of your big K primes could be like a Hamilton double with one horizon on one side and one horizon on the other, and somewhat pure state. I mean, no F prime but in the middle. It's hard to tell if that's true.
Yeah, I guess it's hard to tell if there's a black hole. Like, I don't know, if we just have the tensor network and no kind of, yeah, we don't have kind of, right, yeah, relay CFT. So I guess ruling out a black hole is more difficult. Yeah.
Like what specific set of Python's lunch you're trying to compare to? Because there are definitely, you can set up Python's lunches depending on your access to parts of the boundary, where you don't have black holes, but you still have a Python's lunch. In this situation, yeah, so how does that?
So I guess here we look at this space where you have access to the entire boundary. So yeah, so we're not saying, okay, you have part of the boundary state. Is there a way to distinguish part of this boundary state from part of the other boundary state? We're saying you really have access to the entire boundary state. I think so, based on Netter's paper. But yeah, I agree, it's hard to see. But I guess if you think about a tensor network construction, it's just some layer of tensors where you have, your number of inputs gets bigger than smaller. So, I mean, it's hard to draw it because you have kind of this weird 2D thing, but if you then flattened it out into this picture, on one side you'd have your kind of input kind of bulk degrees of freedom, on the other side your boundary degrees of freedom. And if there's any ring of tensors that has more inputs than outputs, you'd then get kind of a Python's lunch, even though you have access to the whole boundary. Yes, I guess. Sorry, if we go back. So, no, sorry, not this one. This one. So if you think of this as your input, think of this as just a flattening of your entire tensor network. So this is the entire boundary, and this is the entire bulk, and this is just input degrees of freedom. Then, you should be able to reconstruct everything from the bulk. Because the true minimal surface does go all the way back to kind of the actual input. So I guess in some sense, the minimal surface is sort of pushed fully off the page because it's everything. But you do have this you have this local minima. and then, but that's not the true minimum. So this is the local minimum. Oh, so yeah, so we don't have a local minimum in our construction. So that's kind of saying, we don't think our construction has a Python's lunch, which is kind of contradicting the result that, if you have pseudoentanglement, you should have a Python's lunch. I'm not contradicting it because it makes certain assumptions. So it's maybe suggesting there's some assumption that we're violating. Yeah.
Let's say on the starter geometry. This should correspond to some correlation at all these places. Where would this correlate, or how should one say physical correlation that would provide doesn't mean?
So I guess it's kind of some classical correlation. Some classical correlation between these keys, between these inputs. So there's no entanglement necessary between these, but just some classical correlation. Yeah. I mean, we could get rid of it and have these all being different Ks, but then we need to have bigger pseudorandom isometries and, more inputs here. And that would get rid of the need for any classical correlation. It would just mean that here you get a far bigger blow up of the Hilbert space. So here it looks like a big blow up because they've drawn kind of a small example, but in reality, if these are all the same K, you're really only adding a very small amount of randomness at each point.
The problem for physical interpretation or not?
I don't know. I think we'd have to ask the physicists, whether it's better to have it if it's just a classical correlation. Is that an issue? Because I guess we don't say anything about the time dynamics here. It is possible that this classical correlation has evolved slowly over a long time. We're not necessarily saying this has to be some instantaneous property, but it's true it is a very long-range classical correlation. But yeah, maybe the model is more convincing if we instead have different Ks.
My understanding in the traditional Python's lunch, if you have access to the entire boundary, you can reproduce inside the Python's lunch. It's just exponentially hard. But if you sit there and work at it, you get it. Is that true for this if you don't have access to the keys? Or
Yeah. No, you can. With exponential time, you can distinguish the boundary states.
Exponential time, you can determine what the keys are.
Yeah, you can, because it's just all you have to do is try. The possible. So you try the possible isometries, and because you can run them forwards and back. So in our model, we're assuming you're given polynomially many copies of the thing. But if you restrict it to even just having one copy, you can run forwards and backwards until you find the correct key.
Do you understand what is this operation, random pseudo-randomness operation, correct? Or just
Oh, in real gravity? No. So yeah, I think understanding what it would mean to do this in real gravity would be interesting. I guess I'd say, why would you expect it wouldn't? We know that we can do these local operations that create pseudoentanglement in gravity. In standard quantum mechanics. So my question would be, what about quantum gravity is it that breaks that? So I would assume, unless there's some evidence that we can't do that in quantum gravity, that we should be able to do it.
State.
Do you mean like there might not be a single like? Yeah. So yeah. Yeah, I think you might have superpositions over geometries. You might have very kind of highly non-classical geometries. But I guess this construction should apply even if you do have a nice geometry.
If you somehow find a way to time.
I guess the issue with tensor networks is that the tensor network kind of stays fixed. So even if we time evolve, I think if we time evolve, we still won't get a Python's lunch in this picture. But I think we'd have to look at either a tensor network where the geometry is dynamic, or kind of look at real ADS CFT to really be able to rule that out.
Let's see if I understand correctly.
In terms of, if we just forget about ADS-CFT and talk about tensor networks, right? So one way we can have states of high complexity in tensor networks is that we have a Paxos line. Here you're discussing a different way of getting a complex network.
Yeah, so it doesn't actually have high complexity. Like the states themselves are efficiently preparable, but they're indistinguishable from states that do have high complexity. Yeah, if you just have access to the boundary, it's complex to go in the other direction.
Then now we go to gravity. Right? Gravity, the case is that case where there was a friction in the tensor network was easy to interpret. So different areas, and here you would say maybe
There's some other structure we can have in gravity that can generate high complexity.
Yeah.
Roughly like something that in the gravity dual, it's sort of at many places in the, let's say you did a Euclidean path integral, prepare the statement, sort of like in many places in this Euclidean path integral, you might either, add a source or not. That's what the key is choosing, let's say. And so, I mean, the gravity dual is a state like that will have lots of stuff in the state. Right, so then usually we think, I mean, a kind of totally generic one probably has like polarizing features. I think that's what we would probably guess. Of course, some of the states might not have like polarizing, they might not look somewhat complicated in the body. Since there would be like many particles, but probably that's kind of a lower level of complexity than the one you're discussing. That probably wouldn't be puzzling. That would be like the kind of complexity that would be computed by bulk evolution in an obvious sense. But the ones that look like they're the generic ones that look much more complex, probably, I mean, we might guess it would correspond to a black hole because you have too much stuff. Because you allow, in other words, like maybe you get the vacuum state by putting all zeros as the states, right? But then what are these other states where you put non-zeros and they must have some excitation, and then eventually it's too many excitations?
Yeah, I would say, yeah, I mean, I don't think we haven't worked this bit out in detail. I don't think it's crucial for our construction. It's crucial for our construction that we have a full ring of these. It's not crucial, I don't think, that they're at the boundary. So we could move them kind of much closer to the center of the bulk. And then I guess because the center of the bulk, I mean, in these tensor network models, I realize in real ADS-CFT it's more complicated. But we have far fewer excitations. And then, okay, in order for that to work, we need the geometries past these rings to be the same, but we could hide different geometries inside them. And then I guess you need less excitation, so the energy violations are much smaller, you're much closer to the code space. So I think the model is fairly flexible, but we would need a full ring of these so that there is a kind of lower bound on the number of excitations you're adding.
Is the complexity arising from one of the VKs or the fact that you have the many rows?
arising from the fact you have an entire ring and so if you just had one of these rings, it wouldn't work. You really need both in order to.
The minimal model would be just two VK and a VK prime. That's
Oh no, this is the minimal model. You need all of them.
the minimal model is 4, 7.
Okay, so do I have a picture of a? So the minimal model is at some layer of the tensor network, you're having two full circles which kind of cross over like this. So it doesn't have to be at the boundary. You could push it in somewhere, but at some point in the tensor network, you need a full circle of VKs and a full circle of VK primes.
It does feel like you're injecting some noise that'll put a shell of matter there.
Yeah, kind of that, yeah. It's the hardest thing for us to rule out.
Geometry at a time when you don't see the horizon in any obvious way, but it's, you know, if you look at the future evolution, that's somehow, the Python's life is somewhere in the future in the bulk, but that's very hard to see from the describing this particular stuff. Might be the
Yeah, it seems like there could be a Python's lunch if the condition that it should be indistinguishable from R, I feel like in the geometry, that would mean that the region outside the horizon looks like the normal black hole. So this stuff is probably behind the horizon. And if the stuff is a little behind the horizon, then I think the horizon will be this outer minimum surface.
But I think the point is not whether there is a horizon or not, or the point is whether there is a Python's lunch or not. So the whole geometry could be, I think the horizon is a distraction. I mean, there is probably a horizon, but the question is where you can have high complexity without having a Python's lunch. I think that's
But I think if there's a horizon and then his stuff is behind the horizon,
yeah,
then there will be a Python's lunch. Because the horizon will be this local minimum and it will
But
get
it's
bigger and
horizon is
smaller.
extremal in one direction, but not the other direction.
Well, this is some time symmetric configuration where I think we would have maybe a bifurcate horizon, and that would be the outer.
No, but why couldn't it be this geometry, something where there's matter collapsing, right? Producing a horizon and the area of the surface is steadily decreasing. It's not
That could be, but I think that's.
If we can look at the tensor network, we can calculate it. It could be.
Yeah, I was imagining that we put these tensors in the Euclidean past, some high energy operator insertions in the Euclidean past, and I think this will then make something like we could imagine slightly different tensors, but.
Maybe Douglas, I think what you're saying is that like if you take the thermofield double, but then, you know, so say this is the right boundary, and then you put a matter shell that's past the bifurcated horizon, it kind of
Yes.
goes to the.
Well, I feel like that would be the requirement so her tensors are chosen carefully so that the state looks far random to simple observations. I feel like that a way to implement that in gravity is that this stuff should be behind the horizon.
Is the complexity in just the tensors themselves? Just one of the tensors is very complex.
So each of these are log depth. So yeah, each tensor itself is short depth and efficiently implementable.
Are these just a single tensor?
So a single tensor is indistinguishable if you only have access to logarithmic time computation.
Okay, so the simplest one would be just from one of those tensors. So the rest is a distraction. Right?
If you have one of these tensors and you only have access to a very small portion of the boundary, yeah, if you have one of these tensors and you only have access to a logarithmic portion of the boundary, that would be hard to distinguish from another geometry where again you have the same small portion of the boundary. But if you had access to the entire boundary and you just had one of these small ones, it would be easy.
each very simple. Would there be a Python flash inside this tensor?
So inside the tensor, you just have unit trees. And the key, the kind of no additional key, the key is all taken care of outside. There's no kind of additional inputs required. For the discussion later, I think, yeah, there's 3 of the co-authors here. So I think I'll be in the blue room, Lee J will be in the red room, and Umesh will be in the green room. And hopefully there'll be Gravity people kind of spread among all the rooms. So